4:15.
Let's get started.
Okay, yes, let's get started. Hello, everyone. Thank you for coming tonight. Finally, we're getting some warmer weather. Today, me and Richard will be talking about ARM assembly. This is kind of assembly 2 from last semester's x86 assembly. Announcements. Congrats to everyone. Thanks for coming out for DICE CTF. I'm sorry I wasn't there. I was in Oklahoma. But next weekend we are doing LA CTF, which is run by UCLA. We will be in person again. We will commandeer some room and also bring pizza and food and whoever shows up. So keep that on your calendars. Next week it starts February 16th, so not quite right into the weekend, a bit earlier, but it also starts at 10, which sucks, but whatever. I love the West Coast. Anyway, the meeting flag costs an arm and a leg. I did make one challenge for today. I unfortunately was inflicted with the plague earlier this week, so I was not able to make the rest of the challenges. There's a non-zero chance that I will release more challenges later, so if you're interested in keeping up with CTFD, just keep an eye out on that category, because ARM is cool and weird and it keeps showing up in CTFs.
What does the XKCD have to do with the meeting?
There's no good okay, so the last assembly meeting I used the freaking Emacs XKCD, but that would have been like the third time using the Emacs XKCD.
As we speak
But the cute thing is, in ARM there is no compiling, so you never have to wait for your code to compile when you do assembly, because it's just assembly. You assemble it into bytes. Okay, so a small recap on assembly. I highly suggest that if you're not quite there, like check back, scan through the slides on the first x86 assembly meeting. So it's just a human readable abstraction over machine code. So what is loaded into a processor is just bytes, and it parses the instruction to do whatever it needs to do. So for x86, 1 byte determines, the mnemonic or the operation that it actually does. Another byte may determine one or several registers. And in this case, for x86, the next 4 bytes determine the immediate that is loaded into, like, it adds RAX to that immediate and stores it in RAX. All low-level languages will compile to machine code. And so we have those corresponding assembly instructions. On most of your computers, this is x86. Today, we'll be talking about ARM. The processor, of course, maintains the stack, registers, and the instruction memory as the main structures that exist when executing a program. So I won't be recapping entirely how a program runs in this meeting. So we'll go over some background about ARM. What is an ISA? So when we're talking about different ISAs, an instruction set architecture is the specification for what a processor needs to do, what operations it needs to support, and how it manipulates its memory. All right. So if you've heard the term POSIX in terms of Linux, that's it. POSIX is a specification. If you meet POSIX, you have a valid Linux kernel, and so on. In this case, we give you the x86 ISA. If you build a processor that meets that specification, you have an x86 processor. ARM and RISC-V are also other example ISAs. Specifically about RISC-V is it's an open source ISA. So if you want to build a processor in that ISA, take ECE 411. So what's RISC versus CISC? RISC stands for Reduced Instruction Set Computer. Under most cases in RISC, every instruction should take exactly 1 cycle, clock cycle of the processor. And there are separate, distinct instructions for loading and storing from memory, your cache and RAM and whatever. ARM, MIPS, which is the precursor to ARM, RISC-V are all RISC ISAs. CISC is an unofficial term, but pretty much an official term, which basically umbrella terms anything that's not RISC. x86 is a CISC ISA because you have those really long and cursed instructions in x86 that do like 300 things, and then it's like you write it and it just does all the things. But that's what kind of separates it. RISC assembly is very easy to write, but also can be very tedious to write from a human perspective. So what is ARM, the company? It was made in 1980. It was Acorn RISC, but it is now officially Advanced RISC Machines. The most popular RISC format that exists like throughout the world, because Apple likes it. It's in all of your mobile processors and tons of embedded and IoT devices. How ARM makes their money is that the ISA is licensed, which means you can't just make a ARM processor without getting a massive legal team sacked on you. So you have to license the ARM ISA. You can build your processor. ARM collects royalties. Because of how ARM is designed and being a RISC type ISA, they also introduced the performance and efficiency core splits in CPUs. They call it Big Little. You have seen this recently in x86 processors. The most recent Intel generation now has a P and E core split. ARM did Big Little back in the day, which made phones really fast. So what's the difference between ARM and x86? In ARM, everything is fixed with instructions. So you can always expect an instruction to be, by default, 32 bits. x86, you can load 64-bit immediates. That instruction will then just be, 9 or 10 bytes long. There are explicit instructions for memory load and store. So ARM has that dereference operator. x86 has a dereference operator. ARM instead has load word and store word to access memory. Most instructions kind of follow a one destination, two source format, whereas x86 has one destination and one source, and the source is the destination is also used as a source. Richard brought this up that ARM has a weak memory model. Do you want to explain that real quick?
Yeah, so it's not really too relevant for a lot of the challenges, but on a multi-core system, you have different memory models defined by the ISA. So a memory model specifies what happens when two cores running at the same time are trying to access the same region of memory. So ARM has a weak memory model. This means that by default, there could be cases where you have things like going back in time on different cores. It will seem like that from an assembly perspective. So you need these explicit fence instructions to prevent that if you're doing multi-core programming.
Awesome. It also has no segments in memory. This is kind of like those weird registers, pseudo registers that you think of, like the FS and the global segment. This is what it has to deal with us is that stack canaries, there is no segment to store the stack canary, so it's just stored in regular memory. You can end up reading it without too much trouble. So what runs ARM? As I mentioned, pretty much all IoT devices. There are x86 ones, but like all the IoT devices that are used widespread, just like ARM and use ARM. Or if you're in eCTF, you'll know that it is a ARM core with a RISC-V core as well. I think all smartphones that are public consumer use ARM chips. So you're either using the Snapdragon Qualcomm chip or you're using Apple Silicon. Both of those are just ARM. Any Apple MacBook post 2020 with the M1 chips and so on. ARM has also recently, within the last few years, started to get into the supercomputer division. So there are some supercomputers that are all based off of ARM as well. And ARM has had very extensive versioning over the last 3 decades. So when you see ARM v7, v8, that's the architecture version. There's also the core version, which has to deal with what type of core you're using. A lot of the recent ones you might see is like Cortex A7 and 3. And then when we refer to the architecture, if you see AArch64, that refers to 64-bit ARM, and AArch32 refers to 32-bit ARM. So just saying ARM by itself is not explicit. You'll see this AArch come up as well.
Yeah, one thing to add, so in terms of how this actually applies to like sort of running binaries or something like that. If you run file on an ELF binary, it will tell you first of all, the architecture version. So like ARM7, ARM8, and it'll also tell you the like word size. So whether it's 32-bit or 64-bit. The core version really only matters if you're dealing with like specific extensions or if you're interacting with hardware peripherals. But other than that, like all cores that run ARM v7 are going to have the same core set of instructions. And if you've noticed here, the way their naming scheme is solves ARM, application, real-time, and microcontroller. So those are the 3 types of Cortex cores. Who here has heard of Cortex? No. Okay, a few. But that's like their main line of lower end. devices, microcontrollers, with different purposes. Application cores you would see in things like smartphones, and then M cores. I think the ECTF4 this year as an ARM Cortex M. So it's just a little bit of versioning. Okay. Any questions so far about any of these things? History? Anything you guys are curious about? Yes.
What architecture AMD?
x86.
yeah.
That's AMD 64 is based off of the x86 ISA.
Any other questions? Yeah.
Is it because it's reduced instruction set that it only needs 32 bits for the instruction?
Pretty much.
It's a design.
It's a design choice, but like they could have longer width instructions. There isn't really, but there are shorter width instructions, which we'll talk
So you bring up an interesting point. With 32 bits, for example, you can't load something that's 32 bits. Right? If you say, for example, in your assembly file, you want to set a constant that's 32 bits long. Like how do you encode that in 32 bits? You can't, because then there's no more room for all the other stuff in the instruction, like what indicates that it is a load in the first place. So ARM is a little bit more limited in your immediates. You can only load immediates of certain sizes, and we'll see that in the code later on. But there's ways to break that up into multiple loads. Yeah. So any other questions? I see a hand over here before. No. Okay. Yeah.
I was just confused. I want to know, like, since ARM's claim to fame is like power efficiency, how come it's like started to creep into supercomputing applications?
because it's power efficient.
Like a power limit?
When you think about what supercomputers exist as, they're giant warehouses of tons of racks, right? That electricity bill is in the hundreds of thousands, if not maybe grossing on millions. So if I can get a bunch of chips that are power efficient and still performant, which they're kind of hitting because of the RISC type instruction. And I mean, you've seen it with the M3 MacBooks. Like they still, are pretty decent at comparing to other mobile processors. But even in the supercomputing level, cutting down that power cost and subsequently the cooling cost is a big deal, especially at the supercomputing level.
Yeah, just to add on to that, power is correlated with like the amount of heat that a processor will generate. So whenever you have a processor, you also need to pipe out all the extra heat. So that's also a limiting factor, especially in bigger devices, bigger systems. Okay, do we have a question?
For like, so AMD sometimes does use, I was actually at a tech lab with AMD last week, they say they use some like RISC-V, but they used to use ARM as like a startup processor, but that's the only section, like, yeah.
Cool.
Different about it, right?
Yeah. All right, let's move on to the core of today's meeting, assembly. So first of all, this meeting, I know we mentioned a little bit earlier, but one thing that we expect is x86 assembly knowledge, or like vague knowledge. If you've been to that meeting, if not, you can peruse those slides later on. But a lot of the stuff that I'm going to be discussing is sort of comparing similarities and differences to x86. But okay, let's get started. Register. ARM has registers, unsurprisingly. There's 15 registers if you're working with ARch32, 32 registers if you're working with ARch64. One really interesting thing is that actually no, that's sorry. Yeah, so you can look at the table here for the different registers and sort of what they typically use for. This is just something you can have as a reference. One thing I like to point out is the link register, which is R14 here. The link register is how ARM stores the return address when you do a call. So if you recall in x86, when you do a call in assembly, you actually push the return address onto the stack. Now ARM does something different. It stores the return address in the link register, and we'll see in a moment how that affects how our program is written and how our exploitation will differ. There's a frame pointer, just like x86, bunch of general purpose registers. Nothing too complex here. Any questions so far? Yeah, just raise your hand or shout them out as we go along. Be happy to answer questions. Okay, and then for, as I said earlier, AR64, 64-bit just doubles everything. You've got twice the number of registers. They're in different positions. Again, just consult the table when you need to know something. One thing I would like to point out is in AR64, there's 64-bit versions of all registers. And then each register, there's also the first 32 bits is also accessible as a register. So that's what the W registers are. So when you only want the first 32 bits, you would use W instead of X. But X could just mean either. I think X on AR32, which is to 32-bit.
Okay, access like 16 bits.
No, you cannot access the 16 bits. Yes.
So are these like registers more of force convention, or are they sort of just like x86 registers?
All registers are convention.
Okay, yeah, that's right.
Basically these conventions are just like,
Mhm.
this is what you should use them for. If you do something different, we expect you to clean up your register state if you're passing off to a program that doesn't use this convention.
So what does R12 do then?
R12,
Procedural call.
intra-procedural call. So, this is just like, I actually don't know. I can't answer this.
Yeah.
Google it. I don't want to give you the wrong answer.
Yeah,
so
exactly.
yeah.
Let's say that R0 maps to EX, do we use R0 for return?
Yes. Yeah, R0 is return.
Is there any particular reason why they use the link register since in x86 they just use the EIP for calls?
Yeah, that's a great question. Question was like, is there a reason why they use the link register? I think it's just a design choice. You know, you save, imagine you're calling a leave function. So a leave function is a function that doesn't call any other functions. In that case, you don't have to access the stack at all, right? When you call into that function, you save the return address in the link register. When you return, you just branch to the link register. So it saves the stack access. Yeah, it's just different optimizations in different places, right? Okay. So let's move on. I'm gonna go through an example ARM code here. It's gonna be, fair warning, there's a lot of assembly on the next slide, but don't freak out, I'm gonna walk through it. So here we've got a simple program. If you guys can see, just the C code, right? If you look at the C code, it's pretty straightforward. So your laser pointer, there it is. Okay, I'll do this one. You guys are like, let's do this one. Okay, so we've got a main function. It just calls foo. Foo calls nest. Returns bar+2. Give you guys a second to take in this glorious piece of C I wrote. Doesn't do too much, but okay, let's see how it gets translated to assembly. So just looking at the foo function here, and by the way, this is ARM AR64, so this is the 64-bit version. I compiled this on my notebook actually. So it's going to look a little bit different from 32-bit ARM, which I think is what the challenge is.
Challenge is in 64-bit.
It is 64. Okay. It'll look somewhat. So in the beginning of the function, so first of all, a function here always has a prologue and epilogue, similar to x86 functions. I compiled this with no optimization, so it generates some redundant code. The prologue here is going to reserve space in the stack, and it's going to save these like registers, similar to x86. You'll see that this pattern is pretty similar, except we need to store both the frame pointer, which is like RBP, and x86. That saves where the stack pointer was from the parent, and also the link register. The link register, as you recall, is the return address. And at the end here, it loads these back from memory, and then it cleans up the stack. So an ARM assembly, the stores start with ST, loads start with LD, pretty straightforward. And then it's followed by a suffix. So STP means store pair. And then as you see down here, it's LDP, if it's load pair. So Okay, so we save stuff onto this, save stuff onto the stack. And now we want to call this nest function. So if you look at the C code, we're just calling nest with no arguments, right? So that's all it does. It just BL is branch and link. Branch and link. So link means that we're saving the return register when we call it. Yeah, question.
Is a store pointer storing like the stack pointer in X29 and 16 and X30, or storing,
Okay. SDP is store pair. Sorry, not pointer.
or sorry,
store
pair, that's not what to say.
Yeah, so I'll go over this store syntax in a bit, but it's storing X29 and X30 into SP plus 16.
Oh, okay.
That's a good question. Well, there's another slide. Okay, maybe I should go through that one first. Yeah, yeah, I'll go through accessing first. Good point. So we'll do this real quick and we'll go back to the exam. So when it comes to addressing, ARM has like a bunch of addressing modes, which is different from x86. So when the suffix is R, that means just one register. So LDR is just loading one register, SDR is just storing one register. So we can do a normal load. You just load one 32-bit or 64-bit value from one address. That's the first line. Second line, we're storing one value into this R1 plus 2. So you can do an offset. So fairly straightforward and exists in x86. Now the third one here is kind of funky because we're storing R2 into R1 plus 4, but then we also increment R1. So you can see the pseudocode in the assembly comments here. We increment R1 by 4, and then we store R2 into. Does everyone understand that? Any questions? Okay. And then the last sort of syntax is we have a post index, which is where you store, and then you increment. So situations where you would want to have this, if you imagine like a stack, right? A stack, you probably want to either pre-index or post-index, save the value and then increment whatever pointer you have. So it's representing the stack. Or if you're popping, you will load the value and then decrement the pointer. Or depends on which way you're stacking. And then the last sort of syntax is you can also have a shift. So this one gets really complicated. You can increment R1 by R3, but shift it left by 2. That's with the LSL. And then, yeah, that increments and then restore. So ARM has all these addressing stuff because there's no, you can't operate on memory directly. So it gives you more flexibility when you're loading and when you're storing. Any questions? Yeah, the square bracket is dereference. Yeah. So square bracket, generally when you see square bracket, it means you're accessing memory.
But you really can only use these square brackets in the load and store instructions.
Yeah.
So if you try to use them in regular instructions, it will yell at you.
Yeah.
I think in that case, it computes effective address. It does weird things if it works at all.
Yeah. There's also load and store multiple. So this is a really cool thing. I think one of the cooler parts of ON is you can store multiple registers at once. So let's say you want to store like R0 and R1. Instead of writing 2 separate instructions to do that, you can do it all in one go. So you just do this SPM, which is store multiple. And then with the suffix, either increasing after, increasing before, decreasing after, decreasing before. I'll explain what that means in a sec. And then you specify the register where you're either storing to or loading from. So this SP and this store multiple represents the pointer of memory that you're accessing. So this store accesses memory even though there's no like square brackets here. Okay. And then the suffixes determine where how it modifies SP. So if SP has an exclamation mark, that's telling you that it's going to get modified, and it can either be incremented or decremented before or after. So increment before would mean you would first add to SP like the amount of space that these two would need, which would be 16 bytes. And then you would store the 16 bytes of R0 and R1. And then that, so SP plus 16 would be the new SP plus. And then that would be increment before. The decrement is you're decreasing. After would be after. Yeah, keep in mind that the amount it's increasing or decreasing by is the amount of space that these registers would take. So if this is, suppose this is ARC64, each register would need 8 bytes of space on the stack. Together they would need 16 bytes. So it would modify SP by 16, either before or after. And that's how push and pop are implemented, is with these instructions. So in the assembly, sometimes you'll see these just written as push. These are just assembler mnemonics, which just stand for equivalent for some other instruction. Any questions?
So in ARM, are there suffixes for like a long size or a word size or byte size as well?
Yes.
With these suffixes?
Yes. There,
Not with these, not with multiple.
not with multiple.
Or not with multiple, but like just in general.
There are,
Just in
yes,
one
there
of those.
there are load and store suffixes to only load or store single byte, byte, half word, and then on.
Yeah,
Okay.
Yeah, you can do like LB for load and store byte.
that's a good point. So distributor, you can also do, there's also versions of this where you store 1 byte or load 1 byte or 2 bytes or store 2 bytes. You can look up what the mnemonics are for those. That's the same idea. Another question.
So with the SCMDB instruction, if you didn't put an exclamation mark on this next to the stack pointer register, then the stack pointer would not be modified.
Yes, so if there was no exclamation mark, the stack pointer would not be modified.
Would it still run?
It would still run. It would still, the before and after, like increase before and after, increase/decrease after, before, all that would still sort of happen. So it would still effectively increase the stack pointer or whatever, but it would just not write whatever that result stack pointer is back to the register. And this doesn't have to be stack pointer, it could be anything.
Like effectively the page before would.
Now it wouldn't do nothing because it would affect where the registers get written to, if it's a store.
If you had like increase or decrease.
Yeah, increase or decrease after would do nothing. Okay, let's go back to, we'll loop around in a sec, but let's go back to this code segment. So now that you guys have seen some of the addressing modes, that make a little more sense. This STUR just stores a register. I think this stores
Unsigned. What's the
Yeah, store unsigned.
and it's just, so W means it's just storing the 32-bit. Yeah, question.
What's the syntax with the hashtag?
Immediate.
Is
That's just immediate, yeah.
syntax?
If you used AT&T syntax in x86, that would be the
Yeah.
equivalent of using the $sign.
Yes, that just represents the number. So this store is storing W0 into X29 minus 4. So if you look at X29, that's representing the frame pointer for the current stack. That determines where the local variables. No, yeah, question?
Yeah, I was just a confirmation. So ARM data has to be moved from memory into registers before you can operate on it, right?
Yeah, that's
The opposite from x86, where you can operate on whatever
Yeah.
data memory you want.
You can't operate on memory except the load and stuff.
Okay,
Yeah.
also, I'm struggling to know, or I guess I'm struggling to understand why we have different models, like the load and store model. Like, why do we have that as opposed to what x86 has? Like, what are,
Design choices.
Choices.
It's all design choices. Design choices all the way. Because if you think about it, when you have to have like in Operation Dereference, right? How you construct your processor is that it needs to like set these flags and suddenly these instructions start having load and store, which if you recall from 233, accessing memory takes an unknown amount of time, depending on where you're accessing that memory. If it's from your cache, it's fast, but not always one cycle fast. If you're accessing from RAM, it's many cycles. If you're accessing from your hard drive, go get a coffee break. But when you do that, you can't assume that this instruction will be done within one cycle, which from a design perspective prevents you from doing certain efficiency optimizations. Other types of efficiency optimizations exist for x86, but ARM allows you to kind of like batch away loads and stores and let you do other things that aren't dependent on those memory addresses and set everything up and then recover the memory. It just design. It's all design.
Yeah. Do we have another question back there?
No.
Okay. Is there a way to get a pointer? Because I realize people on Zoom can't see what I'm pointing to.
It's a strange.
Is there a
But you
camera?
can't see what he's
No. Like when I was okay. Can you guys see the mouse if I wave it around?
Yes. Okay.
Still getting it?
It's fine.
There's like a Zoom. Okay, that's fine. Let's just quickly go through the rest of this. We branch to this nest function. We return, yada yada. We recover the saved arguments. We compute the value. So this add right here is what is actually computing bar plus 2 arguments. So A0 is W0, which was saved here, is the first argument. So it's bar in this example. It's loaded back into W8 and then add to and stored into W0. So the syntax here is also a little bit different from x86. You you write the result into a different register. So in this line, it means add W8 to 2 with 2 and then store that into W0. Okay. And then you can also like add 2 registers and store the result into a third register. Okay. Any questions about this example back frame? Yeah.
So when we did, look at like load market for store market for.
Yeah.
Is that still one clock cycle?
Depends on how it's implemented. So on a slow processor, it might still be one cycle. If you look at the data sheet, it'll tell you some really small microcontrollers will say everything happens in one cycle because it's so slow that it can go back to memory and back in one cycle. Like it has those guarantees. But you're storing more stuff here, so probably it's not going to be the same time as storing one register on big systems.
It also depends on how the cache is implemented. If it can load a 16-byte cache block, then it can do that in about the same time as one register, since it would load all the data anyway.
Yeah, one last thing I'd point out for exploitation purposes, if your function doesn't call anything, like if you look at nest here, it does not call anything, so it does not ever store the link register anywhere. It just calls return, and return is actually just branch the link register. That's really all it is. So if you wanted to overwrite, let's say there was like a buffer you could write to in nest, and you wanted to overflow it. Well, overflowing that wouldn't let you modify the return address of nest. If we think about buffer overflow exploitations here, that's because there's no link register saved on the stack. So you'd have to overwrite something in foo, like this link register x30, which is saved here and then restored down at 3F70 here. You could overwrite that. That's just something to keep in mind. Okay. So let's move on. Conditional execution. So in ARM, you can do comparisons and then you can operate on those comparisons, like conditionally branch, similarly to x86. But ARM also has conditionally executed instructions. So what this means is you can do a comparison and then do a instruction based on whether or not that comparison, based on like the results of that comparison. So recall from x86 that a comparison sets flags. The ARM has a similar idea here. There's the CPSR, which is the current program state register, the bottom left here. That's similar to E flags in x86. So that just tracks the whether the latest comparison was 0 or signed or something like that.
Negative, less
Yeah.
than, so on.
So that's how the add equal and move less than would know whether or not to do it. So for example, if R1 was less than R2, this move LT would execute. So it would move R10 to R1. And generally the first register is the destination. One thing to keep in mind is that if I modify like R2 at this add equal line, if I modified R2, it would not change the results of the comparison because the comparison has already happened. So
I also realized that I wrote the at equal command wrong. There should be a third register. My bad. R3,
Yeah,
R4,
that-
R5. Whoops. I've been x86.
yeah. I don't know if it would infer 0, which is error, but okay. Do you want to talk about this? Okay. So thumb mode. Thumb mode is where it gets a little complicated and it makes our job as security engineers slightly harder. It turns out this fixed width instruction is a lie. Okay. In thumb mode, instructions are 16-bit in width. So now, first of all, what is thumb mode? Thumb mode is a separate execution mode of ARM. Now, what that means is at any given point in time, your processor will either be executing your regular ARM code or this thumb mode. So this thumb mode, you can enter and exit from it by using these branch and exchange commands. And if you set the least significant bit to 1, it will actually switch the thumb.
Because all addresses are
Yeah.
4-bit aligned. That last bit is used as the file.
Actually, they're all 2-byte aligned because thumb are 2-byte. But yeah, question.
Big endian or like little endian?
A little endian. Yeah. So every instruction is at least 2 bytes because even thumb instructions are 16 bits, they're 2 bytes wide. So all ARM code has to be 2-byte aligned. Now, if you're in the normal like ARM32 or ARM64 mode, those instructions are 4 bytes long, and those have to be 4-byte aligned. So when you put that together, you get that every instruction is 2-byte aligned. So that means every time you do a branch, you have like an extra bit in the first bit, the least significant, right? Because you can never have instruction starting at 1 or 3 or 5. So you can use that bit to encode whether or not the processor should go into thumb mode, and that's what they designed. Very complicated system, but just keep that in mind when you're looking at code. If code doesn't disassemble, there's chances that it could be in thumb. That's also something you need to do when you're writing exploits. For example, if you're calling code that's written in thumb, but you're still in ARM32 or ARM64, then that's going to give you an error. And sometimes that's a very tricky error. So just use branch and exchange, branch link and exchange. That's what the X stands for. That will check the least significant bit of the address and switch to thumb if necessary. Now, yeah.
What does branch and exchange do? I thought you would always have to do branch, link, exchange.
So every branch instruction has like a linking or a non-linking version. A linking version means it saves the next instruction into the link register. The address of the next instruction
Oh, I
into the
see.
link
Okay.
register. So just a branch instruction might be used for something like an unconditional jump. You just want to go somewhere in the assembly.
Like if statements, because there's no reason to remember where you've been in if statements.
Yeah.
You're just branching.
You're just branching. Yeah. And there's thumb 2, which was introduced recently in 2003.
20 years ago.
Yeah. I say this because there's like systems that still don't support thumb 2. Like one of the QEMU processors that it emulates. So there's no like thumb2 support because it was so long ago. But oh, I don't know why that happened. Yeah, question.
What's the point of some?
What's the point? That's a great question. What's the point of thumb mode? It's to make our lives hard. No. The point of thumb mode is to have smaller instructions overall and to have greater instruction density. Now, what that accomplishes is that less instructions for the CPU to fetch, less load on the memory, less load on the cache. That's generally an important thing because fetching instructions takes clock cycles, it takes power. And we want to reduce that by having to fetch less in general.
Not that it is what's happening, but if you think about it, in thumb mode, a processor can be fetching 2 instructions at the same time because in thumb mode, you're fitting 2 instructions at the same size.
Like, would you like write every basic block?
Hmm?
Like, would you basically just write every basic block of that one? Or would it apply?
So in modern, do you have a question?
Yeah.
Sorry. Did you want to say something about this or?
No.
Okay, let me just answer the question first. So in thumb mode, in modern processors, the alignment that comes with regular 32-bit aligned instructions is outweighs the instruction density of thumb mode. So it's really not used as much anymore in larger systems. Like this example I had back here was this was just compiled with stock on M1 Mac. So when you don't optimize for size, it'll just emit your regular instructions. These are going to be not as dense, but that's okay on for systems that have like optimized for this. Now, if you're trying to optimize for size, like let's say you're really resource constrained, you're on a small, very small system, like our eCTF4s last year was like 48 or 200 kilobytes of memory or something, which is not a lot if you want to pack a lot in there. So in those cases, you might want thumb mode or in older processors. Nowadays it's not used as much because especially because of thumb2. So what thumb2 does is that it allows you to mix 16 and 32-bit instructions. So you have some that are 16 and some that are 32. Which is, it's like they realized that 16 bits wasn't quite enough, so they added more, but that which kind of defeats the purpose a little bit.
All things approach variable with instructions.
So that actually slows things down because now if you think about it, to the CPU, when it's decoding instructions, it needs to know where it's aligned. And in order to figure that out, it needs to read the previous instructions and whatnot. So fetching and stuff, that's going to slow it down. So thumb, or really thumb2, I don't think you see much of the original thumb anymore, unless you're working with something pre-2003. But thumb2 is a mix of 2-byte and 4-byte instructions. Yes,
What is the original thumb? Like,
Just 16-bit always.
it's only 16-bit instructions. So yeah. Do we have another question? Okay. Question?
I heard differences in when you're dealing with different architecture settings, like for AR64 or AR32.
Well, both are still using 32-bit instructions. Their AR64 doesn't have 64-bit instructions.
There's no, I don't think there's like an AR64 thumb.
Yeah.
So you still have thumb mode, but I'm pretty sure you're just limited to the first 16 registers, because there's not enough bits to encode all registers. Yeah. Thumb is not really used as much in larger systems, just because the benefits aren't really that big. Okay. Pete, not Pete. Sam.
I am Pete. I am Pete
Sorry.
now. I want to briefly mention at the suggestion of our old president, Robbie, some ARM security features. The point of going down like history and talking about other security features is a lot of modern tasks that you're given if you decide to work in security will be ARM based. people like hacking iPhones for good reasons. So understanding how people are making ARM more secure and why it's harder to break, I give up at this point. Is
the first row stayed on.
is crucial.
Keep talking.
Anyway, so ARM has pointer authentication. Because if you recall that pointers don't use the full 64 bits of addressing space, it's too much memory, too much effort. So they decided to store some info in there and cryptographically mess with the pointers. And so the security extensions allows you to authenticate the pointers upon entering and leaving a function using PAC, IASP, and authenticate IASP. This basically just makes sure that you haven't like messed with pointers in ways that the original program did not intend, which makes ROP harder. There's also branch target identification, which is when you build a program, all of your branches are pretty deterministic on where they're gonna like. It's deterministic of all locations that they're gonna land. So if you want a very secure section, you can branch to basically a landing point, which when executed in sequence is just a no-op. But if you try to branch to something that is not that instruction, the processor will crash out, which makes jump-oriented programming and ROP even harder because you can't go to arbitrary positions. So let's talk about running ARM because there's only a handful of MacBooks in here, I think 3. So if you want to, or maybe 5, there's 5. Okay, I think, there's a program called SIGPwny, which will emulate different architectures. This is all in the meeting flag, so don't worry about copying this down. You can just like do sudo apt install and then this list. You're probably SOL. Good luck. If you have a static binary, you could just run SIGPwny, the architecture, and then static, and then the executable. Static means that libc is just immediately compiled with your program. But if you have a dynamic library, then you need to specify where your linker and libc is located. And so when you install SIGPwny for an architecture, it will put it into your user folder under that name. And then you do -L and run the executable. I think when you install SIGPwny, you also get a bunch of other architectures. So this is not just for ARM. If you do like SIGPwny and then hit tab bash to show you like all the architectures you have installed that you can run. If you want to build a binary in ARM instead, you can use the Arch64 GNU GCC with the bin utils for ARM. But debugging is probably the more interesting thing. So you have to do.
He mentioned Linux, that it only runs Linux if you.
Yes, SIGPwny only runs Linux. So this all works in Linux.
This is user space emulation.
Yeah,
so
this is all user space. There is SIGPwny system, which is slower, and will emulate your whole system, but this is expecting that you're running this in a Linux operating system. So GDB multi-arch is another thing you can just install. This allows you to debug other types of architectures. But it's kind of weird because you're running this SIGPwny program, but you don't want to debug SIGPwny itself because it's doing its own work. So if you run SIGPwny with the -G flag and a port, you can use GDB in GDB multi-arch to connect to it. So you would run GDB with your executable, and then in GDB you would run target remote and localhost. And what will happen is SIGPwny will wait until it gets connected to by a GDB client. And when you run GDB with your executable, they start communicating about where the program is, and then you can debug it, set breakpoints, all that fun stuff. So that's all well and good. Resources, we really recommend this. There'll be other stuff that we'll add to the slide in the next couple of days.
this one is really good.
Yeah,
I
this is extremely good. This is one written from a security point of view. So this page also has tons of other articles that are important for ARM exploitation and debugging. So it's very nice. Next meetings, hopefully HEAP this weekend. We will talk about how to the worst function in C called malloc. and exploit it to all hell and realize why CTF suck because everyone decided peak challenges were cool. And then next Thursday, Akil will be running the ROP meeting, which is basically all you'll need for the rest of your life to do Pwn. Because ROP is very cool. Next weekend, we mentioned again, LACTF, hope to see you there. Hopefully we will have people that will solve Pwn challenges now that we've gone through all of our Pwn meetings. And yeah, all right. I again have one challenge. All it is write a little bit of ARM. It shouldn't be too difficult, but I highly suggest you at least try to like run it locally and debug it locally once just to get a feel of it.
So I had a question about the security feature for branching. So if you have something like executes arbitrary shellcode, right? Will that block something that goes outside of the program?
Probably.
Okay.
Because
Because I was trying to choose like I had a 28-bit bin SA. It was like, oh, this worked. The other assembly thing got killed immediately.
Yeah. So the whole you don't have to have branch target identification on all the time, but if you turn it on in a stack frame, then it's expected that any branches within that operation will be secure. Because obviously there are really extreme cases where you're generating specific addresses to branch to that can't really be figured out by the landing pads. And so it's like, well, this probably is a poorly written program, so it's insecure in different ways. But yeah.
Or it could be like a JIT compile, like a
Yeah.
fast JavaScript engine that JIT compiles code. I might not, want to put in the effort to insert these because these do have an overhead, even if it's very small.
The ideal thing about pointer authentication is that it is a low overhead compared to the previous version, which was stack authentication, which had like a huge like preamble and postamble to do like the same sort of effect. This is just 2 instructions to run.
So is it even possible to do like process injection type stuff on ARM, or does it just get dead in the water?
I mean, if this isn't used, then it's fine, but it depends. It depends on what you're trying, what was implemented by the developers that you're trying to process inject into. There are ways around it if you have enough work and maybe also an oscilloscope.
Yeah, Robbie has done some work on breaking pointer authentication. There's various side channel attacks you can do.
The biggest one he released is I believe Pac-Man was entirely based off of pointer authentication, where you could side channel out the things you need to break pointer authentication by the fact of branch prediction would tell you where a pointer was going to be going and it would break it. And so it like made M1s completely insecure.
Are these features common? Like
In Apple, yes.
and
No,
normal ARM?
They're not common. These are very rare.
All right.
Yeah.
This is every Apple device, maybe.
It's like bleeding edge, like ARM
Is
security.
this analogous to like a control flow guard on Intel?
Yes.
Okay.
This is all to do control flow guarding. Because ROP sucks.
Yeah,
and
yeah.
everyone hates ROP.
x86 has the NBR64. Is that what you're referring to?
I just know on Windows the feature itself called control flow guard. Because if you try to do like, there's some unique tricks you can do, and if you want to do them, you have to actually like have shellcode that adds control flow guard exceptions before you call it. Otherwise, you get blocked.
Interesting.
Any other questions?
Maybe like if you focus on more care about how
Watch Robbie's talk.
Watch Robbie's talk. Briefly, it involves a very lightweight lock cipher, and it takes extra key bits and encrypts each of your pointers.
So I guess like how does it know like a different breaker function?
For branch,
Like where it would be done.
compiler magic. Compilers are extremely complex and will figure these things out on the fly half the time. So it's not really a thing about how ARM and the processor works, is that compilers are very slick at like, computing this for us.
Go do challenges.
The one challenge.
Another good 15-minute meeting.
Sorry.
That was my bad.
Oh yeah, that's right. I was like,
That's funny.
It was like we got to the end of your section and I'm like, I have to.
You know, we started off,
Yeah.
like, oh, only 10 minutes, I'll take my time. And then I stopped talking, I was like, holy shit,
Information,
like,
use practice, the real deal information.
Yeah.
Are these like?
Where's the
Learn
practice?
by doing.
Now we just have to leave.
Okay, it's because it's easier to write 30 minutes of content than to write like a single.
That is.
Yeah. And testing challenges.
If I have more time, I would bring a short look. Yes.
Yeah, well, the big.
That's right.
At least for me, 'cause I'm not just a Docker. but-
You can shift the register. There's also it's different. If you there's a if you remember we talked about that extra extension to LSL